All right, welcome back. So today we'll be looking into wave optics. So this is slightly different from geometric optics that we had been talking about for the previous two lectures. We'll take a look at double slits in interference and then single slits diffraction. Okay. All right. Um, so this is on the aspect of the wave aspect of the light. So again, light is an electromagnetic wave. So then we can calculate the speed of light in vacuum. We use C. For that, it's a constant number. And that's frequency of the wave of the light times the wavelength of it. Okay. And when light enters a medium, speed gets reduced by a factor of n, which is called index of refraction. So then speed of light in the medium, we use normal notation of v, will be speed of light in vacuum divided by the n. Okay. When light travels from one medium to another medium, its frequency does not change, but its wavelength does change. Okay, so f stays the same. Lambda changes. That is responsible for the speed change. Okay. Um, so if we denote lambda, the wavelength in vacuum as just lambda, then the wavelength in medium should be denoted as lambda sub n. Okay, and to line up with the index of refraction. Um, so lambda of n equal to lambda in the vacuum divided by index of refraction. Okay. All right. And then earlier, a couple weeks ago, we mentioned for wave interference, they kind of, when you have two waves meet, they kind of just add up algebraically. Okay. So in that case, y1 and y2, the two waves meet, the total will be y1 plus y2. And so that's for the movement to be adding up. So if you have two identical waves, when they add up, then the amplitude will become twice. The vibration of each point of medium will be doubled. Okay, and then if they are differ by a pi in the phase, then they will cancel out. So this kind of like a shift, you move maybe the second one 180 degrees to that first one. So then the maximum will be here and the maximum from wave two and minimum from wave one, wave two will cancel out. Okay, so that's the case. And wave also interference two-dimensionally as well. So if you have 2D waves when they propagate out, okay, so they can add up at the point the two waves meet. And at the point they meet, so due to the path they travel differently, they could travel in the same distance or relatively small different distance or maybe larger distance. Okay, so it depends on that. So when there's a path difference, then you do see they will add up. So sometimes you have the peak meets a trough on the second wave, peak from first wave meets a trough from second wave, so they will cancel. If a peak meets a second peak, then they will add up. Okay, so similarly. So based on the path difference of two waves when they add up, so again, we call y1 and y2. So if we use sine function, or you could, if you like, you can do cosine function, then we actually add two trigonometry functions up. Okay, so if y1 and y2, they are similar to each other. So by the two sources, you get the two waves generated by these two sources, they meet at point P, okay? So in that case, um, so for wave one from source one to travel there, okay, so it travel x1 distance. So then when this wave produced by source one propagate to point one, P1 here, then we can use this wave function to describe it. For the wave produced by source 2, when it propagates to point 1, you can use this slightly different wave function to describe it. But that's assuming they both have the same amplitude and they are both sine functions, the same frequency and the same wavelength in that case. Okay. So the difference is just x1 and x2. Okay. Now, this second wave function can be written as just the same, similar to wave one, kx1 minus omega t in the sine argument, but plus k of delta x. Okay, so delta x is x2 minus x1 then in that case. Okay, so there's only this guy, which will be the phase difference of these two wave functions. Okay, so k delta x. Now, if k times delta x is equal to 2 pi, then these waves are the same when they arrive at t1. If they are differed by kx delta x equal to pi, then they will kind of cancel out. Okay, so if this is multiples of 2 pi, then a peak will meet a peak, a trough will meet a trough. And if it's differed by just pi, then the peak will meet a trough, and then the trough will meet a peak in that sense. Okay, so they kind of cancel out in that way. Okay, so it depends on the delta, the k times x. Okay, so if k times x, that is multiples of 2 pi. Okay, so in that case, so where k is related to wavelength. Okay, so if you remember, k is 2 pi over lambda. So if delta is equal to 2 pi over lambda times delta x. Okay, so because k is there. Okay, and if that is equal to multiples of 2 pi, so that means this guy delta x over lambda is equal to integer numbers. Okay, so if that's the case, then delta is equal to m times lambda, right? M equal to 0, 1, 2, 3, the integer numbers. Then you will have constructed interference. Now, if that delta x is equal to halves of lambda, okay, so 2m plus 1 over 2 lambda, so n equal to 0, 1, 2, 3, so then the result will be half of lambda, 3 halves of lambdas, 5 halves of lambdas, okay? So then you'll get destructive interference because this thing will give you just the differences of um, 2 times n plus 1 times pi. Okay, so when a wave peak reaches your interest point, then a trough from the second wave will arrive there. So you kind of cancel out in that case. Okay. All right. So with that background, let's take a look at Jan's double slit experiment. So when you have a beam of light hit on this double slit over here, you actually will see a pattern of interference on the screen behind the two slits. Okay, so some places you see interference maximum, that means bright spot. Sometimes you see interference minimum, let's see where you see dark spots. Okay, so in the alternating patterns. All right. And in the lab, you probably use a laser. So you'll see interference patterns. If you use a red laser, this is what you see. Okay, but basically, you have rays comes in and then hit on the two slits, and you'll have interference pattern formed over there. Okay. So in two-dimensional, this can be done also with just water waves. If you drop two stones into a water surface, you'll see two waves will generate and then they will actually interfere with each other. Okay. All right. So let's take a look at the double slit interference over here, and let's take a look at a particular point on the screen here. So point P here, and these two now the rays, they will arrive at the P, okay, but the paths of these two will be different, okay? And normally the screen will be very far away from the two slits. The width of the two slits D compared to L is very small, okay? So then the angle theta here is a small angle. So the only difference is just this small portion. If we zoom in here, as this just small portion of the this ray on the bottom here, that's the path difference, okay? And that's d times sine of theta because this is hypotenuse and then this is approximately a right angle. So this guy will be d sine of theta, okay? And that's the difference. So that's your delta x, okay? So it comes in the equation here, delta x. So d sine theta over lambda times 2 pi. And if that equals to multiples of 2 pi, you get constructed interference where you'll see bright fringes. And then if that equals to just pi, 3 pi, 5 pi, so odd number multiples of pi, then you get kind of distracted interference. You will see dark fringes. Okay. So for the constraint interference, the condition is the delta equal to multiples of 2 pi. And in that case, then delta is d sine over lambda. So for m equal to 0, you see the bright interference at the center of the screen. When m equal to 1, you see the first bright or interference maximum um, aside from the center. Okay, so this is then called the first interference pattern. This is a second interference maximum. This is third, okay, etc. This is called central maximum. So M, so this then refers to which maximum you are talking about in the bright fringes, okay? So M equal to 1 is the first, M equal to 2 is the second, etc. So in this case, 2 pi and 2 pi will cancel, then d sine theta sub m is just equal to m times lambda, okay, for m's order of interference maximum. And if we look at destructive interference, then the delta will be equal to odd number multiples of, so 2m plus 1 times pi. So then d sine theta over lambda times 2 pi is 2m plus 1 times pi. So pi and pi cancels. And 2 will be moved onto the other side, so that becomes m plus 1/2, okay, times lambda. So that's for m's order interference minimum. All right, let's take a look on the example here. So this one says, and then I'm going to switch to here. Okay, so this one says 2 narrow slits separated by 1.2 millimeters are illuminated by light, and that has wavelengths of 600 nanometers. So we can sketch this one here. So there's 2 slits, okay? And so the slit separation, that's D, okay? And then on the screen, down there, okay? So lambda given as 600 nanometer, this is D, okay? And this screen, L, is 2.5 meters away. So it's asking you calculate the number upright fringes per centimeter, okay, on the screen in the region near the center fringes, okay. So let's see here. So it's basically, we will see a lot of bright fringes, okay. So there's a central fringe, okay, maximum. And then there's different orders of maximums on one side, and then also on the other side too, okay. So those are the interference patterns. And then it says how many bright fringes. So you kind of count like how many here, right? And then in the 1 centimeter, okay? So let's say this is 1 centimeter here, okay? All right. So this is your Y. So basically that goes there, and this guy goes there. All right. So we can calculate kind of, this is a small angle diffraction, so the theta, okay? So d theta. So d theta or d sine theta, okay? That should equal to m times lambda, okay? So here theta is related to so if you do y, the 1 centimeter y over L, that actually is tangent theta, right? So theta then is tangent inverse of that. And because it's small angle, so that should be approximated just the sine of theta, okay? And then also approximate just tangent of theta, okay? All right, so that means sine theta is y over sine of theta is about y over L, and that's 1 centimeter over 2.5 meters, okay? And then we know D, so this guy will go in there. Okay. And we can say now in the equation 1.2 times 10 to the minus 3, because that's millimeter, okay, meters, times 1.2 centimeters, so 10 to the minus 2 meters over 2.5, this guy is in meters, okay, equals to m times lambda 600 nanometers, okay, and we can solve for our m based on this equation, okay, so solve for it. This guy will give you actually m equal to about 8, okay, in this case. Alright. So that means within this 1 centimeter range, you can actually find a maximum, okay, because it covers up to the eighth um, interference maximum, okay. All right, so that's on this guy here. And if we go back, now similarly, moving on to the next section, if we shine the light on just a single slit, okay, you will also see um, patterns of maximum and minimum, so brightness and then darkness and brightness, etc. Okay, so at the center you get a center maximum. Okay, and then if we look at the darkness here, one of these lines, okay, then we can draw the two, let's say a particular one here, draw two paths from here to there. Okay, and then there's a difference, but let's maybe divide the single slits into small pieces of small slits. Okay, so then if you get one light ray coming from one of these black dots that represent a slit there, a small slit, it will travel in that direction, and then halfway of the openness of the width of the slits, one half A down there, you get another one there, okay? So when these two light rays meet at the interference minimum, right, the path difference again is this small portion, okay? So that small portion is one half of this hypotenuse times sine of theta, okay? And that should equal to, for the first, if we look at the first minimum, okay, so the first minimum here should be one half of lambda, and then the second minimum will be 3/2 of lambda, okay? So the one half and one half actually cancels. So A sine theta 1 equal to lambda. And normally the screen will be far away from the slit compared to the width of slits. So then tangent theta and sine theta, they are about the same, okay? So for that, in general, then for your um, minimum interference pattern, in this case, we actually call it diffraction pattern, okay, because it's one single slit. A sine theta equal to m times lambda, m equal to 0, 1, 2, 3, etc. Okay, so that's the order of diffraction patterns you are getting, but this is for the minimum, okay, or dark fringes or zero intensities, okay. All right, let's take a look on one example here. It says plane microwaves are instanced on a thin metal sheet that has a long, narrow slits of 5.0 centimeters in it. The microwave radiation strikes the sheet at normal direction instance. The first diffraction minimum is observed at theta equals to 37 degrees. What's the wavelength of the microwave? Okay, so this is not um, light, normal visible light wave here, but microwave and visible light, they are both um, electromagnetic waves. Okay, so they actually behave similarly. So if you have interference, diffraction patterns form for the light, then you also have diffraction pattern form if you use the microwave. Okay, so one single slit there and then a screen down there. So in this case, so it says the first diffraction minimum is observed at theta equal to 37 degrees. Okay, now 37 degrees is not a very small angle. Okay, but for diffraction minimum, we use A sine theta equal to m lambda, okay? And m equal to 1 because that's the first diffraction minimum. So m equal to 1. And we are looking for the wavelength. So then wavelength equal to A sine theta, where A is given as 5 centimeters and sine of 37 degrees, okay? And that will give us 3.0 centimeter, okay, for the wavelength, okay? All right, so that will be it for today. So quickly, we learned that double slit interference for interference maxima. You use this equation. For interference minima, you use this slightly different equation. For single slits, we'll look at just the minimum intensity of the pattern. So it's A sine equal to m lambda. Okay. So that's it for today. We'll come back next time. Bye.